In the previous video, we showed that the error of the output is just a function of all the weights used in the neural network W. And for that very simple neural network we have been using as an example, we have 12 weights in total. So the error is just a function of those 12 weights. And by adjusting those 12 weights, we hope to achieve the goal of reducing the error by as much as possible. Right? We want to minimize the error by adjusting those 12 weights, basically. So if the relation between the error and the weights W is simple enough, right? For example, if in this particular example we're looking at the error depends upon just one weight, and the relation is very simple, right? And for this kind of very simple relation, we can obtain the derivative analytically, right? So dE over dW is just 2 times W subtract 1, right? In this particular simple example, very simple example. And we developed a very simple Python program that allows us to find the best weights that can minimize the error E by taking successive small steps along the negative derivative direction, right? And the Python program for this two-weight problem is almost identical to the Python program we used for solving that this one-weight problem, right? It's almost identical, and the only difference is actually in the function for calculating the derivatives of the error with respect to the weights, right? So for the one-weight problem, it's just a one number, right? But for the two-weight problem, the derivative actually has two numbers because it's got two weights, so it's partial derivatives. We have two partial derivatives, right? So, and this technique of following the negative derivative to reach the best weights that can minimize the error is also known as the steepest descent method, right? And the key ingredient in the steepest descent method is actually the evaluation of the derivatives. So for these simple problems, for these kind of simple problems, those derivatives can be obtained from those very simple formulas, right? Mathematical formulas. And we can actually obtain those mathematical formulas just by hand, or by using some kind of a computer algebra system like a Mathematica or Maple. That kind of computer algebra system allows us to evaluate those derivatives analytically, right? But for our very simple neural network, we have 12 weights in total, and the relation between the error and those 12 weights are already very complex. For deep neural networks, the number of weights can reach millions, and the relation between the error and the weights are even more complex. So the question is, if we can come up with an algorithm to evaluate those derivatives in a systematic way that's sort of applicable not just to those very simple situations, but also to problems of extreme complexity, right? So we will still use our very simple neural network as an example to demonstrate this algorithm. But before doing that, we need to find out the derivative of the nonlinear sigmoid function, which is used inside every neuron to convert the logit z into the neuron output y. So in fact, the derivative of the sigmoid function, so here is the expression for the sigmoid function, right? The derivative of it, so that's fz, right? So f prime z, the derivative of it with respect to z, can be expressed again using the output y, actually, right? Don't forget y is a function of z here. Y is a function of z here, right? So if you bring the expression of y in terms of z back into this expression, you obtain an expression for z, right? So if you make a graph of it, this is fz as a function of z, and this is f prime z as a function of z. So the horizontal axis for both graphs is z, but vertical axis for this graph it's fz, that's y, how y changes with the logit. And here it's f prime z, that's the derivative of y with respect to z as a function of z, right? So that's how it looks like. So now let's evaluate. Don't forget the derivative of the nonlinear function for the sigmoid function, right, equals to 1 subtract output multiplying the output, right? So y is the neuron output, right? Z is the thing that goes into that nonlinear function, right? Y is the thing that comes out of that nonlinear function, and the derivative of this nonlinear function, sigmoid function, actually equals to 1 subtract the output multiplying the output, right? So don't forget about this relation. So we're going to use this relation in our following derivations, right? So that's for sigmoid. The derivative of the sigmoid equals to 1 subtract the output multiplying the output. Right, don't forget about that. It's important. So now let's evaluate the derivative of the error E with respect to the weights W for our very simple neural network. Right. We will evaluate the derivative with respect to the weights in the top layer first. Right. We'll start from the derivatives in the top layer. Right. So let's look at the derivative of E with respect to W211. W211, that's this weight. This weight. W211 that connects Y11 with Z12. Y11 with Z21. Right, this weight. Let's compute this derivative. Right. So the weight W211 actually only contributes to the logit Z21, right? Because W211 is associated with the connection that goes into this first neuron in the second layer, right? If you just look at its subscript, right? The second index in the subscript is the neuron index of the target, right? And then the superscript is the layer, right? So W211 only contributes to the logit Z21, right? So here we can use the chain rule. We can use the chain rule of the derivative. So the derivative of the error with respect to W211 can be expressed as the derivative of the error with respect to Z21 multiplying the derivative of Z21 with respect to the weight W211. Right. Here we introduce a definition. We introduce a new symbol. Right. We define the derivative of the error with respect to the logit. Z21 as delta 21. So here we have introduced a new symbol. So delta 21 just represents this derivative of the error with respect to logit Z21. Right? We call it delta 21. It's just a shorthand notation for this particular derivative. Right? And the logit Z21 is just the weighted summation of the outputs from the neurons in the first layer, and the output that's multiplying with W211 is what? Is actually Y11, right? So the derivative of Z21 with respect to W211 is just a Y11, right? So this derivative can be easily obtained. The derivative of the error with respect to the logit Z21 can be obtained by applying the chain rule again. and it equals to the derivative with respect to the output y21, right? The output y21 multiplying the derivative of the output y21 with respect to the logit z21, right? The derivative with respect to y21, the derivative of the error with respect to y21 can be easily obtained because we have this expression of the error in terms of y21 and y22 here. T1 and T2 are constants. They are true values, ground truths, right? So the derivative of E with respect to y21 just equals 2. We take down the 2 here, and then this 2 that's being taken down cancels out with this 2, right? And then it's just the T1 minus y21. And then you have a minus sign in front of y21, right? So the derivative of partial E partial y21 just equals to minus T1 subtract y21. So this derivative has an explicit expression that's minus T1 subtract y21. Right? And then partial y21 over partial z21 is actually partial y21 over partial z21. So y21 is what? Y21 is obtained by applying the sigmoid function on z21. So partial y21 partial z21 is just the derivative of the sigmoid function, right? So it's partial f, that sigmoid function, over partial z21. And from the previous slide, we know that this partial derivative, actually equals to 1 subtract the output. In this case, the output is y21, the neuron output, multiplying the neuron output, which is y21. So this derivative also has an explicit expression. Right? So if we look at the red boxes, here we actually introduced the definition of delta to 1, right? So here we have obtained, inside of this red box, we have obtained an explicit expression for delta to 1. Right? And the whole thing, including this y11 outside of the red box, is the expression for the derivative of the error with respect to w211. So if we still use the same input values, right, and x1 equals to 12.5, x2 equals to 4, right, and then we still assume the random starting values for all the weights. So all the weights has some kind of random starting value here. We have assigned some random starting values for those weights. Right. Then we can actually explicitly compute this derivative. And for this particular input, 12.5 and 4, this particular derivative has a value of about minus 1.77. So we have obtained one derivative by just applying the chain rule successively, right? And then we obtain this derivative. And we can also apply the same approach to evaluate the derivative of the error with respect to, for example, the weight W212. W212 only contributes to this logit, Z22. Right. So again, applying the chain rule, it equals to partial E partial Z22, multiplying partial Z22 partial W212. And here we have introduced another definition. So partial E partial Z22 is defined as a single delta 22. So delta 22, if we go through the same procedure, the same kind of approach by applying chain rule successively, delta 22 also has an explicit expression that's inside of this red box. And the entire derivative has an explicit expression, including the y11 outside of the red box. And for the same inputs, this derivative has a value that equals to about minus 0.05. So we have obtained another derivative. So these are examples of the derivatives with respect to the weights in the top layer. So what about the derivatives with respect to the layer or the layers that's beneath it, beneath the top layer, right? It's for lower layers. So here let's evaluate the derivative of the error with respect to the weight W111. W111, that's this weight. This weight. This weight. Right. And this weight contributes only to Z11, this logit. So we can, again, by applying the chain rule, right? So the derivative with respect to W111 equals to the derivative with respect to the logit Z11, which W11 contributes to, multiplying the derivative of the logit Z11 with respect to W111. And here we have introduced another definition. Here, delta 11 equals to the derivative of the error with respect to the logit Z11. So all the delta definitions is about the derivative of the error with respect to the logit. And the superscript and the subscript is the same as the superscript and the subscript of the logit, of the corresponding logit. All the deltas is the derivative of the error with respect to the corresponding logit. Right. So now this calculation becomes more complicated than the calculations in the previous slide. So because the logit is just a weighted summation of the inputs, and the inputs multiplied with W111 is actually x1, right? So it's x1 that's multiplied with W111 and then goes into the logit, right? So if you take a derivative of Z11 with respect to W111, then the derivative is x1. Here, applying the chain rule again. We are applying the chain rule again. So the derivative of the error with respect to the logit Z11 can be written as the derivative with respect to the neuron output Y11 multiplying the derivative of the output of the sigmoid function Y11 with respect to the logit Z11. And here again, we can use the explicit representation of the sigmoid derivative. Right? It's one subtracted the output, which is Y11, multiplying the output, which is Y11. Right? So this thing here is actually partial Y11 over partial Z11. Right? That's the derivative of the sigmoid function, represented using the output, using the neuron output. And then partial E, partial Y11 is what? Right? Partial E, partial Y11. We have to evaluate the derivative of the error with respect to the output of this particular neuron. The output of this particular neuron actually goes into two logits. Right? So it goes into Z12 and also goes into Z22. It goes into these two logits. So partial E, partial Y11 actually equals to what? It equals to partial E partial Z21. That's the derivative of the error with respect to this particular logit, multiplying partial Z21, partial Y11. So here we have applied the chain rule again. Right? But it's not enough yet. It's not enough yet. Because Y11 also goes into this Z22. So we have to add this particular term. That's partial area, partial E, partial Z22, multiplying partial Z22, partial Y11. So it's not just a one term anymore. It's two terms adding together. The reason we have two terms is because Y11 goes into these two logits. So it's not just a single dependence anymore. We have two dependencies. Because E, the area E, depends upon Y21 and Y22, right? And then Y21 and Y22 both depends upon Y21 depends upon Z21. Y22 depends upon Z22. So that means E depends upon Z21 and Z22. And both Z21 and Z22 depends upon Y11. So partial E, partial Y11 must equal to partial E, partial Z21, multiplying partial Z21, partial Y11, plus partial E, partial Z22, multiplying partial Z22, partial Y11. Right, this plus, we have two terms. So now we have some terms that's kind of look familiar to us. Because what? Partial E, partial Z21 is exactly delta 21 that we have defined in the previous slide. Partial E, partial Z21 is delta 21. And partial E, partial Z22 is delta 22. Partial E, partial Z22 is delta 22. And for both deltas, we have explicit expressions. And we can just bring those explicit expressions into this particular expression. So delta 21 actually equals to the whole thing inside of this red box. And delta 22 equals to the thing that's inside of this red box. And we can just bring them in here. And now we have obtained an explicit representation of partial E, partial W111. And this expression can also be evaluated using all the numbers that's inside of this particular figure. So these calculations are for our very simple neural network. Can we generalize the calculation to an algorithm that is applicable to neural networks with arbitrary complexity? So suppose we would like to compute the derivative of the area with respect to an arbitrary weight W, which is located at layer L and is associated with the connection between the ith neuron in the L subtract 1th layer and the jth neuron in the Lth layer. Suppose we want to compute this particular derivative. Let's look at the kind of calculations that this weight has to go through. This weight WLij has to go through. Right? So this weight WLij must first multiply with y L subtract 1I. It must multiply with this number. That's the output that's coming from the lower layer. Right? And then this multiplication, this product, contributes to the logit Z, which is in layer L, and it's for the neuron J. That's why the index, the subscript, it's Wij, right? I is the index of the neuron in layer L subtract 1, so it's Yi. And J is the index for the neuron that's in layer L, so it's ZJL, right? So the subscript and the superscript all has meanings, and here they are actually used in a consistent way. And this logit ZLJ then goes into the nonlinear function f In our simple example, it's the sigmoid function, but in a realistic neural network, it could be a different nonlinear function, right? A ReLU function, a hyperbolic tangent function, or other kinds of choices. You could have different choices, right? And this nonlinear function produces the output YJL. So YJL and ZJL, both of them are in the same neuron. And this neuron output is then used as the input to the logits located in layer L plus 1. If we look at this particular simple example, Y11 is used as inputs to the layer that's above it, Z12 and Z22. So YJL is used as actually contributes to the logits in multiple logits in the layer L plus 1. So we can apply the chain rule here. The derivative of the error E with respect to the weight WLIJ equals to the derivative with respect to the logit ZLJ, because WLIJ only contributes to ZLJ. It doesn't contribute to any other logits. It only contributes to ZLJ because the second subscript J, right? They must match. So partial E partial WLIJ equals to partial E partial ZLJ multiplying partial ZLJ partial WLIJ. The first derivative is our definition of deltas. So partial E partial Z, partial E partial the logit ZLJ is our definition of delta LJ. And the second derivative equals to what? Don't forget, WLIJ multiplies with YL subtract 1 I and then contributes to the logit as one term in the summation that's computing the logit. Right? So partial ZLJ partial WLIJ just equals to Y L subtract 1 I. So we have this derivative. So Y L subtract 1 I is the output of the ith neuron in the L subtract 1's layer. So what if L actually equals to 1? Right? In our simple case, what if L actually equals to 1? Then we have Y0 I. In this case, Y0 I actually equals to the input value, xi. So when L becomes 1, when L equals to 1, L subtract 1 equals to 0. So yi0 actually equals to the input, the corresponding input. So how do we actually obtain delta LJ, right? How do we obtain delta LJ? Delta LJ equals to partial E partial Z L. Again, we apply the chain rule. So partial E partial Z LJ equals to partial E partial Y LJ, right? Because and then partial Y LJ partial Z LJ. Partial Y LJ partial Z LJ, we have explicit expressions for it. In the sigmoid case, it just equals to the output subtract 1 multiplying the output. But in practice, it may not be a sigmoid function. So here, let's use another symbol. Let's just use f prime. Let's just use f prime to represent the derivative of this nonlinear function evaluated at z LJ, at the input logit z LJ. And in practice, either for ReLU function or hyperbolic tangent or for any other choices of the nonlinear function, this expression can be evaluated explicitly. So this expression can be computed, and we can obtain a number for this particular expression, as long as the form of the nonlinear function is given. Right? This is computable. This can be computed as a number. You can get a number out of this expression. And then what exactly is the partial E, partial YJL, right? Partial E, partial YJL. Don't forget, YJL or YLJ, not YJL, YLJ contributes to the logits in the layer L+1, right? Maybe not all the logits, but at least multiple logits in layer L+1. So here, again, we have to apply the chain rule, but now with the summation over K. K goes through all the index in layer L+1, the neuron index in layer L+1. And then the stuff that we are summing up is partial E, partial ZK, ZL+1K. The logits in layer L+1 multiplying the derivative of the logit with respect to YJL. And this term in our simple example corresponds to this particular summation here. That's our summation. And comes into this general formula. It is this summation over K. Summation over K. And partial E, partial Z, the logit, right? Z L+1K, by definition, is our delta K, delta L+1K. And partial ZK, ZL+1K, partial YLJ equals to what? Equals to what? Just equals to the weights. The weights that's being multiplied with YLJ. What are the weights, right? What are the weights? Depending upon the K, the subscript K, actually, right? So it's JK. The reason the first subscript is J is because it's from YJ, from the J's neuron in the layer L. So that's why it's got an index of J, first subscript J. The second index, second subscript is related to the K because it depends upon which logit this Y is actually contributing into. Right? So the second index is K. And we sum over all the K. Again, if you have any kind of confusion, you can go back to look at what's actually the W that's being multiplied. Right? So here, partial Z21 over partial Y11. Partial Z21 over partial Y11. That's the weights that's involved is W211. W211, that's the weights that's multiplied here. Corresponding here, that's WL+1 JK. So here we have obtained a relation for computing the deltas in layer L from the values of the deltas in layer L+1, the layer above it. So if we know the deltas in the top layer, say layer capital L, then we can compute the deltas for lower layers successively. We can start with the deltas in the top layer, and then we move down to the layer that's just beneath the top layer, and then move down one more layer, and then go from the top layer gradually to the bottom layer. And we do have an explicit expression for the deltas in the top layer, which is just a minus the corresponding Tj, the true value for the output YLJ, capital LJ. multiplying the derivative of the nonlinear function that's evaluated at the logit z(lj). How do I actually got this particular expression? All you have to do is to look at how we actually evaluated the derivatives with respect to the weights in the top layer. So here you have minus t1 subtracted y21, right? Yeah, minus t2 subtracted y22. That's this term here. And then you have a derivative with respect to the nonlinear function. Derivative of the nonlinear function. That's the derivative of the nonlinear function. That's the derivative of the nonlinear function. That's the deltas. Right. Once we got the deltas, the derivatives with respect to the corresponding weights is just the delta multiplying with y. With a y. Then we have explicit numbers for the y's. Right. When we actually do the forward calculation, that goes from the input, the bottommost layer to the topmost layer, all the y's, the values for all the y's are computed. So here in this kind of a case, when we actually do the forward calculation, going from the input x1 and x2 and also x0, right, with an assumed random starting value for the weights, when we're going forward, all the z's and the y's for every neuron are evaluated. So when we do the forward calculation, all the y values are evaluated. So once we got the deltas from the top to the bottom, we can compute all the weights. So all the weights has explicit numbers for them. And now we have obtained a complete algorithm for computing the derivatives. If you have taken classes in algorithms before, this algorithm for computing the derivatives may look familiar to you. It is actually an example of the so-called dynamic programming. And in the deep learning community, this algorithm is called back-propagation because the derivatives are evaluated from the top layer towards the bottom layer, which is exactly the opposite of the forward calculation, which goes from the bottom input layer to the top output layer.